So here we are again, and still continuing our journey with acids and bases. In this video we're going to be looking at indicators, and you've already used a couple of indicators in class already. So methyl violet, some of you may have used methyl orange or phenolphthalein, or even litmus red and litmus blue are made up of different indicators. So essentially an indicator is made of compounds that change color depending on the environment that they're in. So there'll be one color around a base or a neutral solution, and then there'll be a different color in an acid environment. So they're made up of an acid and its conjugate base, usually, and then the color change occurs over a range of values. So we don't necessarily see a distinct color from one to the other. There'll always be a little bit of range where we might have a mixture of those two colors where it can be a little bit ambiguous. So the color changes and pH ranges for indicators are usually listed, and you get a list of them anytime you're going to use them, and they're given in your data booklet. These are particular ones that you should be familiar with. So with the methyl orange, which we will actually use when we do our titration, we have this situation where if it is in an alkali solution, so if it's a basic solution, it will be yellow. And if it's in an acid solution, it will be red. And in the transition period here, we get this orangey kind of color. Phenolphthalein is a pinky purple color in the presence of a base, and it's clear and colorless in an acid solution. This actually changes around pH 8. And then as soon as it changes into an acid pH, it changes color. So familiarise yourself with those on table 22, and we'll have a bit of a look at some of those as well. So essentially, indicators are made from different plant pigments and different dyes that are usually large organic molecules. And what we mean by that is they're made up of carbons and hydrogens, and usually they have these large ring structures, and we'll look at a couple of them. But most importantly, what it means is that if we have In being our indicator molecule here, when it has its proton attached, it's one color, and when it donates the proton, leaving behind the conjugate base, the In minus ion, it will be a different color in solution. So this one is an example of a indicator called bromothymol blue, and it's blue in bases, but it's yellow as soon as it gets that proton back. So the presence or absence of that proton is what causes the change in color. So we can use that to tell when acid and base reactions have perhaps completely neutralized, or to help us figure out the pH of a solution. This picture here shows you a picture of methyl violet, which is the one that you were using today. Okay, and we can see here that at pH 0 and pH 0, and this would be pH 1 as well, we have this light yellow-green color, and that at a pH 4, it's actually this darker purple pigment. Some of the ones that you looked at in the experiment that you did had this being a blue-green color as it got towards the transition period here. So we can use this for sort of identifying strong acids and weak acids. A weak acid is more likely to be around pH 4, whereas a strong acid like HCl is going to give us a pH closer to 0 or 1. So we'd be able to use this to help us indicate between the two. So there are a huge number of different indicators. You've used universal indicator probably in the past in different experiments, okay? And essentially universal indicator is made up of a whole bunch of these pigments, a whole bunch of different compounds that have these different colors in different environments, so that we get this whole rainbow effect of colors going from the bright reds of pH 1 all the way up to the deep purples and blues of pH 14. And that will give us a whole spectrum of color that we can look at things within the pH scale. This is another way that you might see your indicators being shown, and it shows here that, like with the methyl violet that we were looking at in our lab, you've got the yellow, then you've got this transition-y period here. Thymol blue goes through this red through to orange, yellow, greeny, and then blue. So we can see that these colors change. So it sort of starts to change around here and continues to change here over a range of pH. So it's not an instantaneous pH change from one to the other. There is a range. So we can see here that at around pH 8, phenolphthalein starts to change color at this light blush pink color. Getting darker, the more it changes up to around pH 13. This is another one that we'll be using when we do our titration. We're going to titrate a standard solution of sodium carbonate against hydrochloric acid. And what we're going to use then is methyl orange. It will start off one color and then we're going to titrate through to the other. In this case, we'll start off with the base. So our titration will have the base in the conical flask. So it's going to be this yellowy color, and then we're going to titrate through to this sort of pinky orange color here, which would indicate that our pH has dropped down to 2 or lower. And this is the setup that we're going to use for titration. So essentially indicators allow us to use these color changes to do experiments and figure out when a reaction has started and finished. What we will do is actually have a look at neutralization reactions in particular, and then we're going to titrate to what we call the end point. And the end point is when the indicator changes color. Okay, and we're going to go through, and I'll do another video on volumetric analysis where we storyboard, so we draw pictures showing what's happening and what solutions are in what at each point, and then convert our volumes through. And this will use volume stoichiometry in order to help us work out the concentration of one solution based on the concentration of one that we know. And we will do a titration and a bunch of practice problems in class. But indicators we tend to use in order to let us know when the end point of a titration is. It's one of the key things that we use for analytical chemistry. So I just wanted to go quickly through titration curves. Now you won't have this slide in your printout, but I just want to show you what we mean by a titration curve. So on the axes here, I have on my vertical axis, I have my pH, and on the x-axis, I have the volume of acid added. So what I'm doing is I'm starting, in this case, I have a high pH, so I'm starting with a strong acid, and what this is showing is the gradual addition, sorry, I started with a strong base, because I'm at a high pH, and the gradual addition of acid. So the neutralization reaction is occurring as we add the acid. So we're neutralizing the base, neutralizing the base, neutralizing the base. And then at this vertical region here, this is where we've reached what we call the equivalence point. Okay, so that's where stoichiometrically I've added the same amount of base as I have acid. Okay, and then just a little bit after, I get a change in pH all the way down. So I'm going from a base, neutralized, and then all the way out to the other side of the acid in probably the space of around 1 drop. The more vertical this line, the better my titration. And we can look at where a titration curve starts and ends to be able to figure out where we were. And if we have a look here, this one says strong acid, weak base. If we look at this, it makes sense. A strong acid means that this acid here, when I've gone through my equivalence point, is going to come down to around pH 1. But you'll notice that at a weak base, my pH is actually starting a lot lower than it does for a strong base. And this is because of the partial ionization. So this time I'm starting lower, and our equivalence point will actually be at around a pH of 4 for a strong acid, weak base. Whereas for a strong acid, strong base, we see an equivalence point of around pH 7. In the case of a weak acid, strong base, we can see this is a weak acid because where it's ending is actually much higher, and then our equivalence point is actually going to be at around pH 8 or 9 because the base is going to pull it up a little bit closer towards the higher pH. And then when we have this weak acid, weak base situation, we can see here that we don't have a very vertical region at all. So we wouldn't do this for a titration. We always want to make sure that we have one of them being strong when we do a titration, because when we get a weak acid, weak base situation, we don't have a clear vertical region. So there's no clear point where our indicator will be one color and then another color straight away. So it's hard for us to do an accurate analysis. This one just shows you how we would go about selecting an indicator. So in this one here on the brown line, this line here, what we see is that my equivalence point, I've got that vertical line here. I find the middle point of my vertical line, and this would be a strong acid, pH 1, being titrated with a strong base, which is sodium hydroxide. So as we steadily add the sodium hydroxide, quickly changes pH. Halfway in that point there is my equivalence point, so that would be a pH 7. So in this I could see that methyl orange would not be a good indicator because it's not in my vertical range, and that I could use litmus perhaps. My phenolphthalein is still in the vertical range, so I could actually probably get away with it, but my phenolphthalein is a much better indicator for this one here, where I have a weak acid, strong base, because the middle of that vertical line there is around 9, which puts it 8.72, which puts it in the good range for the phenolphthalein indicator. So in this case, I would choose phenolphthalein for a weak acid, strong base, or I could use litmus for a strong acid, strong base as well. Litmus we don't tend to use for a titration because it's usually on paper, but we could certainly use a pH probe for these as well. So that's a bit on indicators and how we use them. We will do a bit more on this in terms of volumetric analysis and preparation of standards, which will be the next experiment that we do in class.